continuing along, let's review those learning goals that we went through last time. So we talked about the helium atom total energy operator and why it fails, because electrons interact. Okay. Know the Pauli exclusion principle, so both the general and special case. So the general case, kind of what you did in general chemistry, right? No two electrons may occupy the same orbital. And if they do, they must be spin correlated. And the special case is that if we switch the labels of electrons, then the wave function must change signs. Okay? And that leads into a lot more detail that we're not going to quite get into, such as the Slater determinant and how to construct a wave function, an approximate wave function for any closed shell atoms. So just having some familiarity with that is the learning goal. So know how to construct an orbital energy level diagram, so Gen Chem style, right? Building it up from 1s, 2s, 2p, etc. And also know how to do electron configuration for common atoms and ions. Don't worry so much about all of those exceptions in the D block and the F block. I'm not too concerned with those. So just for the commonly occurring atoms and ions. And so I started to touch on singlets and triplets. And then in this lecture, we're going to also talk about doublets. And I'm not quite sure if we're going to be able to finish all these learning goals. I'm keeping my eye on the time. And so if it goes a little long, then I'll split this lecture up into an A, B type situation. Okay, so what is spin-orbit coupling? Well, recall that I've kind of been describing this electron system as kind of like very similar to the Earth, Moon, Sun system, okay? Or really, I should just say the Earth, Moon system, right? So we know that the electron is rotating around the nucleus, and so that gives it angular momentum given by L. But also the electron has its own intrinsic spin, okay? So it is also spinning given by quantum number S. And so we come up with this new quantum number to describe the total angular momentum, which is J and mj, okay? So, and for this very simple system here that I've highlighted, which is all that we're going to get into in this class, we have a high J and a low J. And the high J is given by when both the angular momentum and the spin are parallel, right? So both angular momentums are pointing in the same direction, and there is a resulting magnetic field given by these green arrows that ensues. And that magnetic field is, they're both aligned, and the angular momentums are both aligned, okay? And as we shall see, this ends up corresponding to a higher energy state. Then we have the low J, and the low J is given when the electron is spinning in the opposite direction as it's rotating, okay? And so now you end up creating these competing magnetic fields as well as competing angular momentum, all right? And so J is given by L plus S minus 1 all the way down to L minus S. And mj takes on all values j down to j minus 1 all the way to negative j. And just like we did with L and S, there's total magnitude from the total spin j, and there's also the component on the z-axis given by mj h bar. All right. So let's see here. Did I cover all of my bases? Okay, great. So moving on, let's look at a realistic example. Oh, and then I think that I forgot to give you an equation here. I don't see it written down, and that's okay. I'm not going to worry about the equation. So here's a realistic example. The sodium D lines, and this is the very famous, lovely yellow sodium glow that we're used to seeing in a flame, right? And it's approximately 590 nanometers. Okay, well, as it turns out, when you look at sodium, sodium ground state, all right, and we'll say, you know, sodium solid, 1s2, 2s2, 2p6, 3s1. This creates a doublet. And the reason why this is a doublet state is because we know that we've got this 3s1, there's one unpaired electron, and that electron can be spin up or spin down, and we don't know which is which. Both are acceptable, okay? So that makes the doublet state. Any one electron system makes a doublet state, and hopefully what you remember, any two electron system can either make a singlet in the case of it being paired up, or a triplet in the case of them being non-paired up, like parallel spins, okay? So when we excite sodium, it can go through many transitions, right? But the most notable one is going from this 3s1 to 3p1. And when the electron falls back down from the 3p1 state back to the 3s1 state, so I'll note that by saying 3p1 energy level, 3s1, that creates the sodium D line, that lovely yellow sodium color that we're so used to seeing. Well, as it turns out, because it's a doublet state and its electron spin can be correlated with the angular momentum, as in the high J value, or it can be uncorrelated with the spin angular momentum, the low J value, we actually get two possibilities, okay? And so if you recall, J equals L plus S all the way down to L minus S. And so now if we can see, we're talking about a p orbital, right? So that means that L equals, let's see, 1. And S is always 1/2. So 1 plus 1/2 gives us 3/2 for the high J value, right? And then, of course, it goes all the way down to L minus S. So that means our J can be 1 minus 1/2. So all the way down to 1/2, okay? And the spin orbit coupling is given by this equation, plus 1/2 hc angstrom minus hc angstrom, or A, excuse me, A is the spin orbit coupling constant. So spin orbit coupling constant. And there's a formula for that constant, but I'm not going to worry about it so much, okay? And so what we see, because of these two possible spin states given by the doublet, the 3p1 level is split. And it's split into that high J value, which is actually higher in energy, and it's split into the low J value, which is lower in energy, all right? And so you can see that given here by this term symbol, which is where we're going next. And what's important to note for now, because you don't know about term symbols, here that 3/2, that corresponds to the J 3/2, and here that 1/2, that corresponds to the J 1/2. And so what you would actually observe in that sodium yellow line, if you had a very fine monochromometer or a very highly resolved detector, you would actually see that line as a doublet. There is actually two of those yellow lines occurring at 589.76 in the case of the low J state going back down to the ground state, and 589.16 in the case of the high J state going back down. And remember, because that's a smaller wavelength, it's a higher energy. So there's no way we observe this with our eyeballs, right? We're not going to be able to resolve, what is that, 0.6 nanometer difference with our eyes. There's no way we can do it. And even a lot of the monochromometers that we use, particularly in the general chemistry lab, they can't even resolve this. you have to have a really high resolution detector and monochromometer to tell the difference between these two spins. All right. And what I also want to point out, this term symbol, okay, we're going to use these things as an organized way to note all of these characteristics of the atom, such as what is its J value, what is its spin state, etc. Okay, and so that's where we're going next. So here is our term symbol, okay, and let's walk through it. So up as a superscript on the left, we call that the multiplicity, 2s plus 1, and that gives us the spin state. And we're going to go to all three of these in more detail. The capital letter L, that's our main term, okay? And that gives us total orbital angular momentum quantum number, the total, okay? And then here's the J value, the value of the angular momentum quantum number. And so that's also total, okay? So we're going to go through these one at a time and how we construct them. And I like to compare this to electron configuration on crack. So this is basically electron configuration, but a little bit more difficult. But that's okay. You're chemists and you're senior chemistry majors. We can do this. So let's go. So the first thing that I want to talk about is the main term L. And what I'm going to point out, there's a couple different ways to come up with these term symbols. And most textbooks, of course, go through the super confusing way on how to do it. And that's called this Clebsch-Gordon series. But I'm going to provide an alternative method for coming up with these term symbols that I think works really, really well. So here's this alternative approach, but only if you know the electron configuration. And for ground states, that works just fine. This gets really difficult for excited states, okay? Getting the electron configuration of the excited state. But all the same, let's go for it. So we remember that lowercase l, this corresponds to any one electron. If it's 0, it's an S. If it's 1, it's a P. If it's a 2, it's a D, etc. Okay? The total L value, the capital L, the main term, is given by the Clebsch-Gordon series, which gives all possible values of L. And that goes as L1 plus L2, or plus L3 plus L4, etc., if we had more electrons. And then that goes all the way down to L minus 2, with possibilities of L plus 1, L plus 2 minus 1, and so on. And depending on the number that we get, if we get a total L, capital L, to be 0, we use a capital S. If we get L to be 1, we use a capital P, and then a capital D, and so on. So it mirrors the lowercase l. However, this is our total L value, and we use uppercase letters to indicate that. So for example, let's suppose we have a P2. And what I mean by P2, this is some system that has 2 p electrons. But we don't know where they are. We don't know if this is a ground state. We don't know if this is an excited state, and so forth. So what that means is, and here I'm drawing a picture of this, but we're just saying suppose that's what it looks like. So if we use the Clebsch-Gordon series, we note that both of these p electrons have L values of 1, okay? So my big L is going to go, 1 plus 1 is 2, but then I could go 1 plus 1 minus 1, that would give me a 1, and all the way down to L minus L, that would give me a 0. And so if I look at all of the possible terms, that's an S, a P, or a D. All of those term symbols are possible for any given P2. And so what I mean by that is it could be in this configuration here. It could be with 1 electron on the left, and we skip a block, and then we put 1 electron there. It could be with both of those electrons paired. S, P, or D could correspond to those, and we don't know which one it is unless we know the electron configuration. Okay? So here's the alternative approach. And let's see, I think I have that on the next slide. Yes. So the alternative approach is that capital L equals the absolute value of capital ML. And this capital ML is the sum of all of the ML values. So how do we get the correct ML values? Well, I certainly go through this in general chemistry, that there are actually specified ML values for a given orbital block. But if you didn't do that, here's some review. So S, all ML values are 0. Okay. For P, and this goes in order of how we would list the electron configuration from the periodic table. For P, we start at -1, 0, +1. Okay. For D, -2, -1, 0, +1, +2. And for F, right, you can see it, -3 all the way through +3. So now if I go back here for a second, and I suppose that this is in fact my P2 electron configuration, that I know that that's what it is. So we know now that those ML values are -1 and 0. And if I were to sum up those ML values, right, I'm going to have the absolute value of -1 plus 0 to give me 1. And if L equals 1, then I know it has to be a capital P term. All right? So what if the electron configuration, so I'll make a little key here. So if it looks like this, both up and both up, that gives me a P term. All right? Let's go through the other possibilities. What if it looked like this, where we skip a block? And of course, that would be an excited state, right? Well, we would have a, I'll finish labeling this, -1, 0, +1, all right? So this electron would be -1, and this electron would be +1. -1 plus +1 is 0, right? We don't take the absolute value until we do the final term at the end, okay? Oh, I labeled these incorrectly. Oh my gosh, you guys are probably looking at me like, what the heck, dude? Sorry, the L2 is a D and the L0 is an S, but I got the P right. Okay, my bad. So anyways, this term would end up being an S because the -1 and the +1 cancel to give us a 0. And so then our final possibility would be given by forcing these both to pair up. So then both would be -1, right? -1 plus -1 is -2. And the absolute value of -2 is 2. So that would be our D term. So you can see right away why this Clebsch-Gordon series is a little confusing. Because if we're saying, okay, we've got a P2, it could be a D, a P, or an S. Well, we don't know which one it is because we don't know what the electron configuration is. However, if you know the electron configuration, then you can ascribe what that P, S, and D term is to those particular arrangements. I hope that makes sense. Let's do another example. So here's carbon, 1s2, 2s2, 2p2, right? Same example that I just walked through. And if we do this by the ML examples, and I'll also show you that when I go to add up everything, right, especially with the S block, I've got 2 electrons in the S block here. So that's going to be a 0 plus a 0. And I've got 2 more S electrons in this 2s block, which is another 0 plus another 0. And then finally, here's my 2p. Right, and I remember that was -1 and 0. So that's plus -1 plus 0. And of course, all of that just equals 1, which was our main P term right here, right? So we're just going to use the letter P. And so what's important to note here, we can often ignore the core electrons, the closed shells and closed subshells. Because you note that they all, especially if it's S, right, they're all going to cancel out. So we can often just look at the valence electrons to get the correct term symbol. All right? Okay, so let's move on to the next terms. So multiplicity, which is this chunk right here. Okay? And there's a couple ways that I like to do this. So for one, here's our Clebsch-Gordon series, right? And these little s's correspond to the electrons, okay? And s can only be 1/2 for an electron, right? So when you start going through these possibilities, depending on the number of electrons that you get, there's only certain values that you're going to have. Basically 1 or 1/2 or 0. Okay? So let's go through that. And so this is for any 2 electron system. Okay? So we have singlets, doublets, triplets. Or, not any 2 electron system, my bad. Any 1 or 2 electron system. Because a doublet is a 1 electron system. Okay? So if we have a singlet, we know that a singlet describes a paired up set of electrons. Okay? And if you go and calculate S for this situation, you get S to be equal to 0. Oh, so excuse me. So S plus or minus 1/2, right? Okay. So both of those cancel out. S is equal to 0. And if S is equal to 0, 2 times 0 plus 1 is 1. And so on my main term here, if I wrote 1, and then I'm just going to write L and J, that number 1 tells me I have a singlet. So we don't have to do this 2s plus 1 if you already know the electrons are paired. If you already know the electrons are paired, that's a singlet, and we can automatically just put a number 1 right there. If we have a doublet, S is equal to 1/2, right? Only 1 electron. And so 2 times 1/2 plus 1 is 2. All right? So there's our doublet. That would just describe a singly unpaired electron. And so we would automatically just write a 2 right there, L and then J. And then obviously we would have a P or another letter for the main other terms. Okay? And if we have a triplet state, we have 2 electrons plus 1/2 plus 1/2. So I'll note that just as this. It could certainly be minus 1/2 and minus 1/2, but we take the absolute value. And so what that means is, yes, we would then have S is equal to 1. 2 times 1 plus 1 is 3. And so literally, if we knew that it was 2 unpaired electrons, we wouldn't even have to go through this. We could just write triplet as a 3. 3 triplet means the same thing. Okay? So now finally, what about the J value? Well, J also has a Clebsch-Gordon series, which is given by all values capital L plus capital S all the way down to L minus S. And so that means if you have a situation where you have like D, P, and S as possibilities, you get an awful lot of possibilities for the J value, okay? So I'll go back to those P2 examples we used, right? We looked at 3 different P2 examples given by this, okay? And let's just go through all of those. So we remember now that when they're both paired up, D is the main term, which comes from an L equal to 2. When they were split all the way like that, oh wait, let me double check, apologies. Yes, so S, because it was -1 and +1, so that cancels. Okay, so this is the S term from L equal to 0, and this was our P term from L equal to 1, okay? So now that means in my terms, if I look at this here, so this is a triplet, right, because they're unpaired. So I could write that as triplet P. And now, because I've specified the fact that it's a triplet and a p, right? So triplet corresponds to s equal to 1. So then I could get a triplet p2 as my term symbol. However, I could also have a triplet P1 and a triplet P0. And as it turns out in spectroscopy, the 2, 1, and the 0 state for that don't really matter all that much because we don't have any spin-orbit coupling, spin-orbit splitting to deal with over here, okay? Well, I suppose that's only partially correct. So because, in fact, if both of those electrons were both spin down, then that would be important. So what I meant to say was the triplet P1 state becomes less important because it's this triplet P2 that's really describing both of them being up, and the triplet P0 that's really describing both of them being down. However, these still really aren't observed to create splitting that we observe in doublet states when you only have one possibility, okay? So now if we go to these S possibilities here, we recognize that it's an S. It's still a triplet, okay? So now that means, so S is equal to 1 and L is equal to 0. So the only possibility is, or excuse me, there are two possibilities, 3s1 and 3s0. And now finally, if we look at this D state, we've got the letter D right there. We recognize that this is now a singlet because they're paired up. So S is equal to 0. And so now I could have a singlet D2. I could have a singlet D1 and a singlet D0. Okay? And so once again, we typically for, I'll say for the non-half values of J, that value is less important. So when we see a non-half integer of J, and all of these are non-half integers of J, oftentimes people just discard that term right there because it's less important for spectroscopy. However, when we do have J 3/2 or J 5/2 or J 7/2 even, those terms are important and they're often included, okay? So what I want to do, I've got several examples to go through, and I've already been talking for about 28 minutes. So I'm going to stop this video, and I'm just going to record another video going through all of these possibilities, or at least some of them. I'll go through a big chunk of them, and the terms that we get, okay? So I'll see you in the next video for going through examples of these term symbols.